Good afternoon, everybody. Welcome to this test of time session. My name is Yves Robert. I am a professor at École Normale Supérieure de Lyon in France, and I was chairing the test of time for this year. The annual test of time award recognizes an outstanding paper with lasting impact and that deeply influences the HPC discipline. The rule of the game is very simple. There is a committee, this year composed of 11 members, whose name you can check on the SC24 planning webpage. And this committee selects the best nomination. Anybody can nominate a paper, including the committee members, of course, provided that this paper has appeared at SC at least 10 years ago, and at most 25 years ago. This year, the test of time awardee is GPU for HPC computing. It is co-authored by 4 authors, all from Stony Brook University in New York. And today on stage, we are very fortunate to have 2 of them. The second speaker will be Dr. Zhe Fan, who was a PhD student back in 2004 when the paper was published at SC, so exactly 20 years ago. And the second co-author will be our first speaker, and I'm happy to welcome on stage Professor Arie Rosenberg, who was by then and still is a professor, a distinguished CS professor at Stony Brook University, New York. Please welcome Professor Kaufman.
Thank you very much for the kind introduction. This is this Totai award. It's really a great honor, and I'm truly humbled. I received many awards in my academic life, but the proudest of this one, this is a result, because this is a result of a historic impact or revolution in computing. The presentation today, I'm going to present about half of the talk, followed by the presentation by Zhe Fan, my former student. Dr. Zhe Fan works today for Waymo, autonomous cars, and he was the primary developer of the technology, assisted by another PhD student of mine, Feng Qiu, who is now working for Siemens Medical, and as well as Suzanne, who was my postdoc at that time. She's working now for a startup, Mission Focus. So this is the paper, our supercomputing 2004 paper, GPU cluster for high performance computing. The paper was conducted under my supervision, and it was somewhat my idea, and that's what I'm going to present now, how we developed this technology, what brought us to develop this kind of an approach, as well as some applications that we included in the paper to prove that this is really a doable and efficient technology. So a little bit of background. The technology was developed at the Center for Visual Computing, or CVC, at Stony Brook University. I founded this center in 1996 and directed it until today, until this date. The primary research areas of the center was primarily graphics related, visualization, a major focus in volume rendering, hardware accelerated volume rendering, including GPUs, but also hardware that we developed and also licensed to Mitsubishi Electric and Japan Radio Corporation. Other application has been medical imaging, machine learning for imaging, virtual reality, graphics, visual simulations, and visual flow modeling. This is primarily important because that's what actually led us to the dual use of the GPUs, using it for computing. So we were looking at accelerated volume graphics for mission planning. So this was a project funded originally by Hughes Aircraft. We built for Hughes Aircraft a voxel-based flight simulator. And you can see in the pictures, one of them is a fighter going through the cloud, which are gases or amorphous phenomena. These are basically flow applications. A second one is a battlefield visualization with clouds in the sky. The third one, the bottom left, is fire and smoke in the battlefield. The middle picture at the bottom is Camp Pendleton with haze. Again, amorphous phenomena that we had to simulate in our project. And the picture on the right is a workbench, a virtual reality workbench that we were using for the Navy application. The second part of this project was funded by ONR, the Office of Naval Research, primarily for battlefield visualization, but we did also mission planning, command and control, and things like that. They liked the workbench, which looked like a sand table that allow you to design, have several people around it and design the application that they wanted. Anyway, so this was the two applications that used volume graphics for mission planning, and we wanted to accelerate it. Why we wanted to accelerate it? Because the application called for real-time flow phenomena. They wanted real-time clouds, real-time smoke, real-time fire, real-time gas and plumes of gas and things like that in the battlefield. So how do you do real-time visual flow modeling? So we started with Navier-Stokes equations, but these model macroscopic behavior of flow. We could have done this with Navier-Stokes equations, but the numerical solutions are extremely slow because it has a nonlinear term. Instead, we adopted the Lattice Boltzmann method. This was a relatively new technique. When we started, it was probably 10 years old. So in physics, this is extremely, extremely new, but we tested that, and it happened to be that LBM, Lattice Boltzmann method, is easily parallelized on multiprocessors. But it wasn't fast enough on multi-CPUs. So we had in the lab GPUs and GPU clusters, and we tried it on our GPUs, and it happened to be running fast enough for our application. It was running in some cases up to 100 times faster. So this was our GPU cluster. It was called Stony Brook Visual Computing Cluster. It was built around 2002, 2003. Originally, we built it for graphics applications. So this was, you can say, graphics HPC. And later on, it became a dual-use cluster. We used it for graphics HPC and computation HPC. Originally, we built it with 40 nodes using NVIDIA GeForce FX 5800 Ultra. That was a relatively expensive GPU at that time. And, but the entire cluster, if I recall correctly, was about $35,000. So we built this HPC for $35,000. And then we used this for our supercomputing 2004 paper. But for the paper, we used only 32 out of these 40 nodes. So GPU background, I'm sure most of you know a lot about the GPUs. Now they are commonplace. But at that time, we didn't call it GPU, we called it commodity graphics hardware, because we developed also other alternative graphics for similar applications. But this was our commodity graphics hardware. It has a lot of data parallelism and high memory bandwidth, including memory on board, on chip. It has simple caches and simple control flow. But it was originally built for a very specialized applications of real-time rendering of 3D graphics. The pipeline of GPUs is pretty simple. I guess now it's pretty simple, but at that time it was pretty complex. We start with a mesh of a 3D object. We go through geometric processing, or sometimes called vertex processing, and projection, and you get your geometry in 2D. You rasterize or pixelize this into a set of fragments or pixels, and you map texture and lighting onto this fragment. You get a colored fragment in the frame buffer, and you then can convert it onto the screen. That's the graphics. That's a GPU. Again, this was originally built for graphics, and we built our cluster also just for graphics. We also did some groundwork before we built it, before we used our cluster for the flow applications. So this was actually a pioneering work we did with a single GPU that laid the foundation for the 2004 paper. We had two other papers that I listed here. We had several of them, but these are two good examples. The first one was led by my student, Xiaoming Wei, and she developed the Lattice Boltzmann modeling for visual simulation and how to do that on a GPU. The second one was accelerating Lattice Boltzmann on graphics hardware using register combiners, but that GPU was a fixed point arithmetic GPU. So the simulation did floating point simulation using fixed point arithmetic and was still running faster than the CPUs at that time. So this was two examples of our groundwork that led to the Supercomputing 2004 paper. So this was we were part of this movement called GPGPU. The term was coined by Mark Harris, who was a PhD student at UNC. Now he works for NVIDIA. And there are many, many applications that we're running on GPU. We tested Lattice Boltzmann models. Others tried linear algebra, matrix computation, and things like that. The motivation was somewhat simple. There was rapid performance growth of the GPU, which was much faster than the Moore's law. That's what you see in the graph. The bottom blue one is more or less Moore's law, but the green curve is what is sometimes referred to as Wang's law. Jason Wang of NVIDIA coined this term, and this you saw a tremendous growth, performance growth of GPU as compared to Intel CPUs. It was also attractive price-wise, and there were newly added features. At that time, we were primarily happy that the floating point was added to the GPU, and also you could program the GPU using high-level languages. We primarily used the CG shading language at that time to do our work. So what was the motivation for our Supercomputing 2004 paper? Of course, our pioneering work that I mentioned to you, two of them in GPGPU on a single GPU. The GPU price performance that I showed you on the previous slide, and new features that were introduced there. Also, the Navy application that we did for real-time flow modeling, we did it on a single GPU, and it was really promising. And also our strong belief that the GPU would soon become predominant for computation. The results for computation, like matrix computation, and the work we did with LBM were very promising. And also the belief that GPU clusters will follow this trend into the HPC. And therefore, we put together our Supercomputing 2004 paper that we call GPU cluster for HPC. So the impact of our Supercomputing 2004 paper, I'll talk a lot about NVIDIA. I have 0 shares of NVIDIA, so I have no interest in NVIDIA. So first, the impact is we were the first to document and build a GPU cluster and develop several applications, practical applications, that show how attractive the performance of the GPUs is for HPC. This is also an early step of this historic GPU computing revolution, and we think this was, and indeed, a major impact of this paper. Then what are the monumental? This computing revolution was indeed a monumental one. As you can, all of you know and see now that the GPU is taking the major part of the new AI applications. Data center, 74 of the chipsets in data center are GPUs used for AI applications. And NVIDIA has 92% of the market share of GPUs. And according to them, now GPUs deliver 95% of peak performance of supercomputers. This includes the Oak Ridge Summit. And finally, this is relatively new. I checked online a week ago, and a week ago, NVIDIA was still the world's largest company by market valuation, surpassing $3.6 trillion. Apple is unhappy about that, but that's okay. So we practice now in our lab, in our center, CVC center, what we preached in or advocated in 2004. We have almost 200 GPU cluster. These are all NVIDIA RTX, 6,000, A5000, A6000. And what we are very proud or happy about is the fact that it's still a dual use. We have HPC for graphics and HPC for AI. The HPC for graphics is driving an immersive virtual reality environment called the Reality Deck with more than 1.5 billion pixels. Billion with a B, billion pixels. And we also run a lot of AI applications on these almost 200 GPU cluster. So, as I mentioned before, we used several applications, flow applications in our paper to confirm and attest to the fact that this is a good idea for GPU clusters are a good idea for HPC. This is in addition to the Navy application that I mentioned before. All of these applications are accelerated on our visual computing GPU cluster, all using Lattice Boltzmann, and they were all developed around 2002, 2003. And I will invite Zhe Fan to present all these applications.
Thanks, Arie.
Thank you.
Okay. The application that Arie let us work on was open security. So this work was supported by Environment Measurement Lab of DHS. We obtained a 3D geometry model of the Times Square area of New York City. This contained 91 blocks and 850 buildings. So the goal was to simulate the airborne contamination dispersion in this urban environment. A challenge is that the complex 3D shape of the urban environment. So this is where the airborne came in handy. The airborne is a computational fluid dynamic model, as Arie already mentioned. It discretizes the 3D space to a lattice. On each lattice cell, there are 19 velocity vectors. So associated with each velocity vector is a floating point value called a particle distribution. This particle distribution models a probability of finding a particle at the location with that velocity. The airborne computation involves some simple steps. First, all the particles, a collision of all the particles are computed based on a relaxation equation. Then after collision, all the particle distribution needs to stream to the neighboring cells. Although those rules are very simple, the airborne was theoretically proven to recover the Navier-Stokes equation. The airborne has some advantages. The first advantage are all the computation are local. By that, I mean, in order to compute a cell, you only need the data in that cell and the data of the neighboring cells. So this is a highly data parallel computation and hence is well suited for GPU acceleration. Another advantage is that airborne can efficiently handle the complex moving fluid solid boundary condition. So this makes it attractive for urban simulation. So we first implemented the airborne on the single GPU. Unlike the previous work that Arie just mentioned, with this work that used the hardware register combiner. At that time, we were able to take advantage of the newly available GPU features such as the high-level CG shading language, as well as the floating point capability. So we organized the airborne lattice to 19 volumes, and then flattened those volumes to the 2D textures. And we implemented all the computation operations as the OpenGL rendering steps. All the computation code were implemented in a series of CG shaders. So our GPU implementation was 7 to 15 times faster than our CPU implementation. On top of that, we developed a novel voxelization method to efficiently compute the complex moving boundary between fluid and solid. The end result is a closed-loop simulation happens very fast on the GPU. All computation, all visualization just happen on the GPU. No data needs to leave the GPU. So we were able to let animated objects interact with the fluid dynamics happen in real-time speed. And I recall this was a lot of fun during this research. Then we started the GPU cluster implementation. We divided the whole grid into subdomains and assigned each subdomain to one GPU. During each simulation step, the particle distribution at the surface of the subdomain needs to stream to neighboring subdomain. So this results in the communication among multiple GPUs. The data will read out of the GPU, transfer through network with MPI, and then write into other GPUs. The key takeaway in our work was that we found that GPU computing is fast. So the communication was the key bottleneck, and our focus was mainly on the optimization of this communication. The first optimization we used was contention-aware communication schedule. Before the optimization, each GPU needs to send a lot of data as secondary to nearest neighbors. But it also needs to send a small amount of data diagonally to the second nearest neighbor. We simplify this pattern by only allowing each GPU send the data to its nearest neighbors. The small amount of data that needed to be sent diagonally was sent in 2 steps indirectly. We found that this reduced the likelihood of collision on the Gigabit Ethernet and achieved better network performance. Another optimization we did was simply let communication happen in parallel to some computation. The idea was we first compute the surface or the cell at the surface of the subdomain. Then we can run the communication, and in parallel to the computation, we compute the interior cells of the subdomains. When the number of nodes were under 28, we were able to fully overlap communication cost with computation. So in other words, the communication didn't impact the performance of the overall simulation. When the number of nodes were more than 28, we were only able to partially overlap them. So we started to see the impact to scalability. So we simulated when in this Times Square area of New York City, we ran a grid on 480 by 400 by 80 on 30 GPUs, achieved a speed of 0.3 seconds per step. This performance was comparable to the latest work at that time on supercomputers. On top of the wind simulation, we simulate the dispersion of the airborne contamination, as well as the smoke in the Times Square area. Then we compared the performance of our GPU cluster with that of our CPU cluster. We did a scale-up test, let each subdomain to be cubed, and then scale up the whole simulation domain when more nodes were added. As shown on the right figure, on average, our GPU cluster was 5 times faster than our CPU cluster. This was pretty exciting to us, but what was more exciting to us was that we saw a lot of room for future improvement. We list some of them here, but for the time's sake, I will just highlight a few of them. At that time, one limitation of the GPU is reading data out of the GPU was very slow. It was an order of magnitude slower than writing data into GPU. Fortunately, very soon, newer generation of GPUs already addressed this problem. Also, we noticed that at that time, it soon became possible to put multiple GPUs on each node, and this would significantly reduce the network load. Another interesting limitation of the GPU at that time was it had a very small memory. For example, the GPU used in our cluster only had 128 megabytes memory. We reasoned that if future GPU gave us larger memory, not only it would allow us to simulate a much larger grid, but also it would improve the scalability because it would increase the ratio of the computation cost to communication cost. This is because we do the computation for the whole volume, so that's order of n cubed. We only do the communication for the surface of the subdomain, which is n squared. So if memory increase, n would increase, and the ratio of computation to communication would increase as well. Okay, so we already talked about our SC2004 paper. After that paper, we continued our work on the GPU cluster. One extended work was thermal fluid dynamics in a pressurized water reactor in a nuclear power plant. So the context was during emergency, high pressure cold water needs to be injected into the core in order to cool down the core. A concern was an excessive injection of cold water could cause a thermal shock. In other words, the high temperature gradient could cause the vessel to fail and hence damage the vessel, cause a much larger accident. So the goal of this research led by Arie was to use thermofluid dynamic simulation to help experts to do safety analysis. A challenge of this work was now we had a irregular shaped simulation domain. It would be very wasteful to use a cuboid grid to run the simulation. We developed an efficient way to pack the irregular shaped simulation domain on 16 GPUs by storing the indices of all the cells, all the neighboring cells of each cell. In addition, we used the hybrid thermal LBM based on the multi-relaxation time model. This model was much more stable than the previous LBM and hence can handle the thermal dynamics. And this is the results that we simulated and visualized on the GPU cluster. Another work that we spent a lot of time work on was called ZP. This is a framework that we developed to simplify GPU cluster programming. The idea was we borrowed the global array concept invented by the Pacific Northwest National Lab. This provides a simple interface, n-dimensional global arrays allow the developer to easily move or copy data among the GPUs. But we also exposed the data locality information to the developer so that they could the data efficiently and move the data efficiently. In a short summary, the ZP framework abstracted the GPU cluster in two most important characteristics. The two-level parallelism hierarchy and the non-uniform memory access. And then we developed 3 example applications based on ZP. The first example application was sort-last volume rendering. The second one is the matching cubes as a service computation. The third application, we re-implemented the LBM with ZP, and it was much simpler than our first implementation. Now, we are going to conclude this talk. The primary contribution of our SC2004 paper was that this was the first documented effort that built a GPU cluster and developed a practical application showcasing its efficiency and cost effectiveness. The key lesson we learned in this work was that GPU computing is fast. Hence, usually the communication optimization is the key to success. We were very fortunate to become one of the early pieces of a very large GPU computing trend. Today, we are seeing companies building huge GPU clusters, such as with tens of thousands of GPUs, or even with 100,000 GPUs. But 20 years ago, Arie decided to build the first small GPU cluster. I think his pioneering vision was the key element of our paper, and he deserves major credit. With that, we would like to thank the Test of Time Award Committee for this prestigious award. We are really humbled. We would like to thank the original reviewer of our paper. We would like to thank many colleagues, friends, and organizations for the support to our research. And thank you, all the audience, for your attention. Thank you very much. Let me invite Arie back to stage for questions.
I'd like to thank the author again. We are running a bit late, so I suggest we take questions off the floor right after we close this session. But I would like to add a final comment. I do remember that 20 years ago, when we were planning the future exascale machines, we were envisioning up to 1 billion cores with a B, as Arie pointed out, and it never came true, fortunately, because of the GPUs, whose introduction was game-changing for the HPC community. So I'd like to congratulate again the authors for contributing to writing the history of current HPC supercomputers. With that, I'm closing the session. Thank you all for attending, and thanks again to our authors.
Thank you. Thank you.